In this video, we're going to describe the electric field of a uniformly distributed sphere of charge. This means that the charge is evenly distributed throughout the entire sphere, not just on the surface. So we're not talking about a conductor here. Here would have to be some sort of insulator, which has been uniformly charged everywhere on the surface, inside. Every part of it has the same amount of charge and the same amount of volume. We haven't looked at what the electric field looks like of that inside and out. So this is another example where you can see a problem whose solution is going to be a formula, not a value, and that's the primary output of Gauss's law. And Gauss's law is going to be the tool by which we solve this problem. So let's start by drawing what it looks like. In this case, we have a sphere that has charge evenly distributed everywhere in it. And I'm going to imagine a Gaussian sphere. So the sphere that's black is the actual physical sphere. And the Gaussian surface that I'm going to use, again, that's just the surface I use for Gauss's law, will be done in red. And it'll be another sphere of variable radius. I'll call this radius r, and the radius of the sphere we'll call A. Now we'll look at two cases. What happens if r is greater than A, and what happens if r is less than A? In the case that r is greater than A, then all of the charge is inside here. And I'll just call the total amount of charge capital Q. Well, this is pretty simple. If I look at Gauss's law, then what I find is that for this object, the area is simply that 4 pi r squared, because it's the surface area of the sphere. And cosine theta again is 0, because the electric field is going to have to be directly outward or inward, and the strength cannot depend on where it is along the surface. It's just as strong here as it is on the far side. So, as in previous examples, I get is the enclosed charge over 4 pi r squared times epsilon naught. If r is greater than the radius of the sphere is greater than the radius of the physical object, then all of the charge is inside of the Gaussian surface, so therefore it's just capital Q. So the enclosed charge in this case is just the total charge Q. So then we just have the formula we had before, which is Q over 4 pi epsilon naught times r squared, or as you could also write it, K Q over r squared. So that's nothing new. What's interesting is what happens on the inside, because when you go to a smaller radius than A, what you find is that not all of the charge is inside. So the enclosed charge is now less than Q. So how much? Well, I said it had a uniform charge density. And I'll call the density of charge rho, which is just Q, the total charge, divided by the volume of that sphere. In other words, that is Q divided by the volume of the sphere of radius A is 4 pi over 3 A cubed. So, in this case, the total charge enclosed in it is going to equal to the density times the volume of this smaller sphere. And in that volume of that smaller sphere is going to be 4 pi over 3 r cubed, because that's how much the volume of this sphere is. This volume is of the whole sphere. Now if I plug in here for rho, the enclosed charge is equal to Q times 4 pi over 3 r cubed, but also this factor, which is 4 pi over 3 a cubed. And these factors of 4 pi over 3 cancel, leaving the enclosed charge is equal to the total charge times r cubed over a cubed. So if I plug that over here into the electric field formula, here I have that it is q r cubed over a cubed over 4 pi r squared epsilon naught. And some of these powers get canceled out, leaving me with q r over 4 pi epsilon naught a cubed. Or in other words, kqr over a cubed. So this means that the electric field actually gets stronger with a larger radius. So if we looked at how strong the electric field was, it'd be 0 in the center, because r would be 0, get larger and larger and larger and larger until it hit the surface at A, and then it get weaker and weaker. Well, if I plotted it as a graph, the electric field versus r, it would go up in a straight line, and then at A, it go down like 1 over r squared. So the largest magnitude electric field is at that surface right here.